zeta omega n t by under root 1 minus zeta square into sine omega dt plus theta. Okay. All right. So now let us go ahead. So for various values of zeta and various values of damping ratio, we have seen the response of a system. Okay. Right. So now we are in the process of characterizing the second order system. Characterization means few parameters which you require to describe the behavior of the system. So few parameters what we have discussed is rise time, delay time, peak time, overshoot, settling time, and steady state error. So these are the parameters which we came across. So I think next week you have mid exam.
Yes, sir.
Starting from Monday or which day?
22nd, sir. Yeah.
Monday. Monday is
Tuesday.
20, no?
Tuesday, sir. Monday is 21.
Tuesday means we are not going to get any hour. Tomorrow is the last hour, I think, right? Right. So then I think we by this time we have to finish the second chapter. Okay. Right. So rise time. So we need to get the derivations for these parameters. So I'll quickly go through it. Right. So this is for omega and various values of omega and how the response is going to change. And these plots you have to plot using MATLAB because once you finish your examination, then I think we can go for MATLAB session. So last week I think Dheeraj asked me, I think sir, if you want to take, you can take on Saturday or Sunday. He told me, but I think that was I didn't plan. I was out of station, so I couldn't do that. So these plans you have, these plots you have to plot. Okay. Right, using MATLAB. So now coming to the rise time. So how do you define rise time? Rise time is defined as the time taken for the response to reach 10% to, so that means we have three systems. One is undamped system, one is underdamped system, one is critically damped system. Right. So for various systems we define rise time differently. So generally we can take rise time as time taken for the response to reach 100% of its final value. For underdamped system, 10% to 90% its final value. So then to get a derivation, what we should do? Tell me any one of you quickly. So underdamped system, 10% time taken for the response to reach 10% to 90% of its final value. So then what we want C of TR means rise time. So at 10%, what is the time is what we have to get, and 90% what is the time we have to get. Then 90% to 10% time is what we have to subtract. Then we get rise time. Is it not? Yeah. So instead, what we can do is we will try to find out the time where the response will reach 100% of its final value. Is it fine? Is it okay?
Okay, sir.
Yeah. So then what we need to do, C of t is 100% means what we have to substitute here at C of tr? At rise time, the C of tr is how much? 100% means? One, no?
Yeah, 1, sir.
Yeah, it's 1. So you substitute 1 here. Okay, you substitute 1 here and then try to simplify that response for the time is tr. Okay, so we have to get the expression for tr. Okay, so then now if you further simplify this, right, so e power minus zeta omega n tr can't be 0, so this term is equal to 0. So when you try to make it 0, right, so when you try to make it 0 and if you try to simplify this, So cos omega dtr plus zeta by under root 1 minus zeta square sin omega dtr is equal to 0. So the above equation we can write it as sin omega dtr is equal to, right? So just simplification, right? So then tan omega dtr is under root 1 minus zeta square by zeta, right? So then tr is omega dtr is tan inverse under root 1 minus zeta square by zeta. So is this fine? No, these steps are okay, right?
Yes, sir.
Yeah. So then omega dtr is 1 by omega d tan inverse step, right? So now if you try to see this, so this is omega n zeta omega n, and then this is j omega d. So now if you try to find it out, this is omega n under root 1 minus zeta square, and then this is omega n. Okay, then from this if you try to find it out, okay, so tr is, okay, tr is pi minus theta by omega d. All right. So the expression for rise time is pi minus theta by omega d. So we will be using this particular equation for rise time from now onwards. So if any second order system is given, right, and if so what is theta here? This simplification error.
Yes, sir. Yes, sir. Like because of the minus pi minus theta by WT.
Theta is cos inverse zeta, no?
Yes, sir.
Okay, right. So this is what the rise time, no. So this is what the expression for rise time, right? So theta is tan inverse A by B, right? So this is what we will get. So then this is what expression for rise time, right? Rise time. Okay. Then next parameter, we have transient response parameters. So rise time, peak time, overshoot, settling time. These four are very important transient response parameters. Okay. So now if I try to find out the peak time, so what we should do now? Tell me. So this is what the expression. To get the peak time, what we should do? Peak time is, how do you define peak time?
Time at which it will reach the highest point.
Highest point. So to find it out, what we should do?
Substitute the highest value of C of t.
Now see, this is what the reference is what we want, correct? No. So d by, to find out where it is maximum, right, and then the minimum, then what we should do? D by, so at that time this is 0, right?
Yes, sir.
Okay. So if you try to find out this particular expression, d by okay, so dc of t by dt, if you try to find it out, so if you try to derivate this with respect to time, and then now if you equate to 0, then at that time you will be getting the expression for TP, right, peak time. So now, so you are equating this to 0, right? And then if you try to simplify this, okay, if you try to simplify this, so it everything, you know, this is what should be there in your mind. Right, so this term, you know, this is there, okay, right? So from this only you are going to get the substitution. So now tan theta is a by b. So now anyhow it is a and this is b, right? So from this one is what we are trying to write it as, you know, theta, right? So pi minus theta by omega d. So similarly here also, you know, if you try to find out for the peak time, so now this is what the uh, derivative is what we are finding when then we are trying to equate to 0 to find out the maximum peak. And if you try to, you know, simplify this further, omega d is omega n into under root 1 minus zeta squared. So under root 1 minus zeta square will get cancelled, right? And then now if you try to further, you know, simplify this, okay, if you further, you know, if you try to simplify this, so this term is having zeta omega n and this term is having zeta omega n. And now if you simplify this, then you are going to get this particular expression, so where e power minus zeta omega n t can't be 0, so then this particular term is 0. And now if you try to, you know, simplify this, so you are going to get peak time as sine omega dt is equal to 0. So this is the time at the peak time. So what would be the expression for peak time now? So so t and the possibilities at which this will happen is 0 or pi or 2 pi by omega d. So then we will write it as Tp is pi by omega d. So is that fine, all of you? Peak time expression.
Yes, sir.
Sir,
This
zero
is
should
what.
not be there, no, sir.
Huh?
Zero should not be there, no, sir. At zero, it will be zero.
Yeah. Pi to pi n. Pi by omega d. So then we have to find out overshoot. So overshoot, you know, how do you find out? So this is, you know, these derivations are very important. I think if it is online exam, I think I may not be asking, but if it is offline exam, you know, you have to do it there itself. Okay. So now to get overshoot, what we should do? So this is what overshoot, right? So this is this particular part minus this part, correct, right? So then, you know, we are going to get, this is what C of TP, right? And then this is at C of infinity by C of infinity, the maximum overshoot is where it touches. So C of TP is what is this, okay? And then now if you try to find out, you know, C of infinity is 1. That means at infinity time, okay, it is going to become 1. So this particular expression minus 1 by 1, if you try to, you know, further simplify this, then overshoot is what you are going to get it as. So just, you know, simplify, maximum overshoot is e power minus pi zeta by under root 1 minus zeta square. So this overshoot is expressed in terms of percentage, right? So overshoot for a given system, whether it is 10% or 20% or 25% or 60% or so on. Okay, so this is a simpler expression only. Now you see the C of Tp minus C of infinity by C of infinity means, you know, this is the peak time. So this minus this. So this it will reach at what time? At infinity. Right. So C of infinity is 1. That means, you know, the response is going to reach the required input at infinity. So C of infinity is 1. So C of Tp minus C of infinity by C of infinity. Right. So this is how you try to find it out. Overshoot is. Okay. Overshoot is. or 1 minus C of Tp is also you can write. Or C of Tp minus 1. Is it not? C of Tp minus 1. This is what the given response, right? All right. This minus this, right? Is what overshoot. So anyhow, this is 1. Okay. So C of Tp minus 1 is what you are going to know. If you try to try to simplify it further. Okay. So you are going to get this particular expression. So omega d is omega n under root 1 minus zeta square if you can substitute. So then you are going to get overshoot as e power minus pi zeta by under root 1 minus zeta square. So very important, derivations. Okay. And the formula we'll be using in our. So then this is what the settling time. So how do you define settling time? Tell me how to derive now. We have seen 3 derivations, right? We have C of t. So for finding out settling time, what we should do? How do you define settling time? Yeah, if I want to get the expression for settling time, what should be done? Tell me. Settling time is
98
defined
to
as.
102% allowable.
Yeah. Tell me. Advait?
Time to reach 98% to 102% of final value.
Yeah. So, some certain systems, 2% error is allowed. Certain systems, 5% error is allowed. It means time taken for the response to reach 98% of its final value or 1 or 2% of its final value and stay there. Right. So that is what we need to find it out. So then what we should do now? So C of t, what we should keep? To find it out, the time, settling time.
So it should be in the range of 0.98 to 1.02. Like that.
1.02. So that means we have to find out the time at which the response is 1.02. And we have to find out the time at which the response is 0.98.
Yes, sir.
And the 1 or 2, that time minus this time is what settling time, right?
Yes.
So that is what the derivation. So now here we have, under damped system, the pole is minus omega n zeta plus or minus omega n d, j omega n d, omega n into under root 1 minus zeta square. So the real part contribution is exponential decay, and the imaginary part is what the oscillation is in the entire response. So settling time is 2% criteria if you try to consider. So time consumed in exponential decay up to 98 of the input. So you try to go for the derivation. So 98% means you will going to get 4 by zeta omega n. So settling time is what you get is 4 by zeta omega n, and 5% means 3 by zeta omega n is what you get. Okay. So you just verify this. Derivations are there. You can find it out. So settling time is 4 by zeta omega n. So these are the important characteristics parameters or transient response parameters for second order system. So now we have seen rise time, pi minus theta by omega d, peak time, pi by omega d, and settling time 4 by zeta omega n for 2%. Okay, and for 5% it is 3 by zeta omega n, and maximum overshoot is e power minus pi zeta by under root 1 minus zeta square. And there are tools when you try to do it with the help of MATLAB, and there is a separate toolbox called control system toolbox is what it is developed. So the moment you write a command, it will find out all these values for a given system. Yeah. So now let us try to solve few problems based on this particular concept. So You keep in mind, so keep in mind, now we have the second order response, right? And we discussed the underdamped response, right? So here is Chandaluri Abhiram is there. Abhiram. Upset. Prajwal. Prajwal. Okay. So now we have undammed systems, underdamped systems, overdammed system, and all. Specifically, we are going to underdamped system, and then we are going ahead. Why? What would be the reason? Anyone? Tell me.
Because the zeta value will be 0 to 1 only, sir.
For which systems?
Underdamped.
Underdamped system.
All real-time systems are undamped systems, or critically damped systems, or underdamped systems.
Underdamped.
Underdamped means the moment you give input, you get a certain oscillatory response in the beginning, and then it will attain a final value. All real-time systems are underdamped systems. So we are restricting our study, okay, mostly to underdamped systems. Okay, right. So now, so we have the total time response can be divided into transient response and steady state response. Is it not?
Yes, sir.
So steady state response. So few parameters we derived here, few parameters we need to do. That is what I am going to do in the next class. So the steady state response is what I try to take up in the next class. So in steady state means the time taken for the response as time t goes to infinity, how the system behaves is what we can try to take up in the next class. But in this class, let us restrict to this transient responses. Okay, right. So consider the system shown in figure where the damping ratio is 0.6 and natural undamped frequency is 5 radians per second. Obtain the rise time, peak time, maximum overshoot, settling time. Okay, when the system is subjected to unit step input, you can do it, right? What is given? Zeta is given. What is given? Omega n is given, correct? No. If you want to find out TR, what do you do? Omega d is what? Omega n into under root 1 minus zeta square. So omega n is there, zeta is there. How to find out theta?
Tan and
Cos inverse zeta.
Cos inverse zeta. Okay, so you can do it. This is direct, simpler. Direct, substitutional problems only. You can do it. Okay. So this is what the rise time. Okay. So 0.55 second rise time and peak time and settling time, so 1.33 second. Okay, and then maximum overshoot. The moment you try to find out the maximum overshoot, you are going to get in this case as has not done, I think, but you can finish it on this. Right. So this is what the given. For the system shown in figure, determine the value of V. Velocity feedback constant means I need to cover settling time response parameters too. Okay. Yeah, so this kind of problems would be asked. Okay, so this is what simple mechanical system, the mechanical vibratory system, right? And then the response of the system is given like this. Determine the value of M, B, and K. B means damping constant, K is what spring constant, M is what the mass, so is what you have to try to find it out from this. So this is what 0.1, and then this is what 0.009 feet. Okay, so from this, you have to apply and then you have to find it out. So this real-time problems. Yeah. So this is what we will do it. We will try to solve a few problems. Right. So now step response of critically damped system. Critically damped system means when zeta is equal to 1. When zeta is equal to 1, then we can write this as omega n square by s plus omega n whole square. And R of s is what? Unit step, which is of 1 by s. Okay, omega n square by s into s plus omega n square. So when you try to find out partial fractions of this, a by s plus b by s plus omega n plus c by s plus omega n whole square, and try to find out the coefficients a, b, and c. Okay, and then when you try to find out the inverse Laplace transform, then you are going to get this. C of t is 1 minus e power minus omega n t minus omega n e power minus omega n t. So can anyone tell how the response will look like? Do you have any oscillatory terms here? Second order system.
No, sir.
So it is exponentially increased one or exponentially decreased one. That means what? You excited a system with unit step response. Correct, no? So you would be getting a response like this, or you would be getting a response like this.
Increasing.
Increasing.
Increasing. Yes, sir.
Increasing. Okay. So that means, as the time t goes on, so as the time t goes on, right, and it will meet the desired response at somewhere else. Okay. So now, how do you define transient response? What is transient response?
From starting to the time before the steady state response.
Steady state. And then when the moment you give input, the system will undergo some changes. Is it not? The
Yes, sir.
system will undergo some changes and it will remain its allowed range of the final value. Correct, no?
Yes, sir.
So this is called transient response, and this is what called settling means steady state response. So when you try to plot it, so e power minus 1 minus e power minus omega n t by 1 plus omega n t, right? So this is what critically damped response is, right? So now by keeping this in background, so now let us try to do few problems, okay, from our Kuo book. We have, we have 20 minutes of time. So chapter 5 is time response analysis. Yeah, so if you now try to see 5.1, 5.2, so all the problems are involving steady state plus transient response time. So here, if you try to see, there is calling it as type of a system. Determine the step ramp. So now 5.3, if you try to see, determine the step, ramp, and parabolic error constants of the following unity feedback control system. So this is error constant means it is steady state response point only. So then I think I need to cover that and then come back to the problems. Okay, so see when find the position, velocity, and acceleration error constants for the system given in figure. Yeah, so that means I need to cover. So now let me finish that also. Steady state response also. Okay. I'm taking help of online material which is available. Yeah. So now let us try to see the control systems and control system steady state response point of view. So steady state response point of view means we have to find out limit t tends to infinity c of t. Is this called steady state response? Yes or no?
Yes, sir.
Can we find out this limit t tends to infinity c of t? Can we find out this? Is there any remedy for this? So we are applying Laplace transform and we have final value theorem. So then to find it out, so that means we have to get the response, steady state error. So that means we are interested in when you give input whether the output will reach to the desired one or is there any error. So this error is what we try to find it out, which is called steady state error. So steady state error can be called as limit t tends to infinity c of t. Right, but now everything is available in terms of S domain. Okay, we are applying Laplace transform. So what the final value theorem of Laplace transform says? To find out this, what we need to do? Come on. ESS is limit S tends to 0 See here, we are going to see the steady state response. Steady state response means only one parameter is what we are going to consider in steady state response, which is called steady state error. The steady state error, how do you define? So now if you have a control system, okay, a system is described by its transfer function g of s, and you are giving feedback, negative feedback, and now you have input r of t, and we are trying to analyze c of t when time t tends to infinity. So whether the output will reach input or not. If I design a motor with 1500 rpm, the finally it reaches 1500 rpm or not when t tends to infinity. The meaning is that, right? So now here we get error. Error is nothing but what? R of t is nothing but what? Sorry, E of t is nothing but what? Tell me here in this case. Error is
E of t minus R of t.
yeah, it is C of t minus R of t or R of t minus C of t. Anything is all right. Right. So this is what the error. So now we want to see this error is going to become 0 or not. 0 or not means we have to find out limit t tends to 0. Right. We limit t tends to 0. Sorry, limit t tends to infinity C of t. That means limit t tends to infinity. How this error is going to change is what we are going to see. E of t, C of t minus R of t, and t tends to infinity, E of t. So then steady state error is defined as limit s tends to 0, S E of s. Is it not? To find out steady state error, if you apply final value theorem of Laplace transform, yes or no? Getting or not?
Yes, sir.
Yes, sir.
This is what is called steady state response. And similarly, how we got characteristic parameters in transient response, steady state response to have parameters like steady state error. So steady state error is limit t tends to infinity E of t, but we can't find it. So then we will be using Laplace, final value theorem, which says that ESS is equal to limit s tends to 0, S E of s. So this is what we have to get. But before going to derive this, okay, before going to derive the steady state error, we have transfer function, right, which can be given by time constant form like this, k by, right, so k by 1 plus sta, 1 plus stb, so on up to it's a ratio of polynomials s, numerator to the denominator, right? So sometimes you may have possibility of getting or poles at origin of order n. Listen carefully. The transfer function may involve poles at origin. That would be 1 pole or 2 pole or 3 poles. Right. So now if you have, how do you define order of a system? How do you define order of a system? Now we are discussing second order system. Means what? Come on. Tell me.
Maximum degree in the denominator.
Maximum degree of the polynomial s in the denominator term, right?
Yes, sir.
Yeah. So now here we have other form, which is s bar n. So which we call it as type of a system. So here we will be using two terms. One is called order, another one is called type. Okay, we will be using two terms. One is called order of the system, and another one is called type of the system. So now if I have a transfer function, g of s is equal to 1 by s plus 1 into s plus 2. So how many poles are there at origin here?
At origin, there are no poles inside.
No poles. Then this type of systems are called type 0 systems. Okay. Right. So if you have transfer function 1 by s into s plus 1 into s plus 2, how many poles are there at origin?
One pole.
One pole. See, this is what pole 0 map. Right. Pole 0 map. So pole, here, here you have one pole at origin, another pole is at -1 and another pole is at -2. Is it not? These poles are indicated by using cross mark. Right. So this is type 0 system. Now, if you have one more transfer function of a system, which you have here 1 by s cube into 1 by into s plus 1 into s plus 2. What is the type of a system? Type 3. Right, type 3. So the type of a system will influence the steady state response of a system. I'll come to that point little later. Okay, so now you understood what is type of a system. What do you mean by type of a system?
A number of poles at origin.
Number of poles at origin. So now if you try to see open loop response of open loop transfer function, see here you have a system like this. This is what G of S. So now G of S, if it is like this, 1 by s cube by s plus 1 into s plus 2, the type of a system is 3. Right. So if there is a closed loop, you are now you are incorporating feedback for better response. Then open loop response means this only, right? For open loop transfer function, the number of poles which lies at origin describes the type of system. I hope you understood this, correct? So this number of poles at origin will influence steady state response. How that is and all, we will try to see now. So now if you have a transfer function, generalization, so S bar n and all, so you can write this. Okay, you can write this response of a system like this. Okay, generalized form. Keep this in mind. It involves the term S bar n in the denominator representing n poles at origin. So a system is called type 0 or type 1 or type 2 if n is 0, n is 1 and n is 2. So that is what we discussed. So as the type of a number, the type number is increased, accuracy is improved. However, increase in the type number, so that means how that is and all now we will try to see. Yeah. So now let us try to take steady state response and then try to derive the expression for E of S. So now if you try to take listen very carefully, 5 minutes only. All right. So now you have C of S, R of S and error. So C of S by R of S is G of S by 1 plus G of S. Right. So now we are trying to find, so this is what the closed loop response. Okay, so this is what the closed loop transfer function. So then E of S by R of S. E of S by R of S. So we are going to steady state response. How do we define? So steady state response is defined as limit S tends to 0. Yes, E of S is what we said. But if you want to get E of S, right? E of S. So what you can do now? E of S is R of S minus C of S, and C of S is what? E of S into G of S. Correct, no? So now if you try to get the expression for E of S, so E of S is 1 plus G of S. Yes or no? So E of S is what? E of S is
R of S by 1 plus G of S.
it is R of S by 1 plus G of S. Understood? No? This point is clear, no? Now, so this is what error. And we want steady state error means what we do? Limit S tends to 0, SE of S. Is it not? Okay.
Yes, sir.
So now, let us try to derive this. We have 5 minutes of time. Quickly we can do. So E of S. So limit S tends to 0, S E of S. So steady state error is ESS is limit S tends to 0, S E of S, and limit S tends to 0, S E of S is what? R of S by 1 plus G of S. Correct, no? Right. So now R of S can be a step input, it can be a ramp, it can be a parabolic input. If it is step input, R of S is 1 by S. Ramp 1 by S square. Parabolic 1 by, right. So now the error, the steady state error is going to depend upon the transfer function G of S. Okay. Now, so now if the given transfer function is having 1 plus STA, 1 plus STB, right? Time constant form is what it is written, plus so on up to 1 plus 1 plus ST, what is the generalized form he has written? Yeah, so ST1 and A, B and all, yes, what is it? Okay, anything is fine. Right. So 1 by ST1, 1 plus ST2. So which order system is this? Order is okay. Order, the order would be N here, order would be, M here, zeros here, M. So generally we try to take N is greater than M. Then it is called proper transfer function. Okay. Right. So now, which type system is it?
Type 0.
Type 0.
0.
So here we have cases type 0, input can be step, correct? It could be type 0, input could be ramp, correct? Input can be type 0, sorry, system can be type 0, then input can be parabolic, correct? No? So we need to know the steady state error in this case. Case number 2, type can be 1, input can be step, is it not? So type can be 1, input can be ramp, correct? Type can be 1, input can be parabolic, correct? Case number 3. So type 2, input can be step. Type 2, input can be ramp. Type 2, input can be parabolic, correct? So, okay. So now let us try to derive. We have means we have different types here and different inputs here. So now let us try to go ahead with so we will fix this or we will fix this. Which will fix? Tell me. Type is what we fix or input is what we fix? So I am trying to take case. I am fixing input step. Right. So input I am fixing it as step and various values I am trying to take type 0, 1, 2 and so on. Okay. Right. So now input is step means R of S is equal to 1 by S. And now I am trying to take type 0 system. That is what the case. So then what is ESS? Right. So type 0, the first case I am trying to take. ESS is limit S tends to 0. Yes, E of S. E of S is what? R of S by 1 plus G of S. Right. If G of S, if it is type 0 system. Right. So if it is type 0 system, so limit S tends to 0. Yes, R of S is 1 by S, 1 plus G of S. So what is the steady state error? Limit S tends to 0.
Sir,
Yeah.
is R of S into G of S.
Why R of S into G of S?
Sir, because C of S by R of S equals to G of S upon 1 plus G of S.
Here, see, I have derived this, no? E of S, we are trying to find out E of S, Nama, which is R of minus E of S. E of S is E of S into G of S. So E of S is R of S by 1 plus G of S, no?
Yeah, yes, sir, sorry, sir.
Okay, so this is R of S, yes, R of S by 1 plus G of S. So SS will get cancelled. So steady state error is limit S tends to 0, 1 by 1 plus G of S. Right. So now when you try to take it out, this has 1 by 1 plus limit S tends to 0 G of S. This is what the steady state error expression. Correct. So now G of S, if it is type 0 system, so now I consider type 0. So type 0 means there is no pole at origin, right? So type 0, right, type 0. So when I consider the it is type 0, then now if I am trying to write it as 1 by 1 plus Kp, where Kp is a positional error constant, so which is limit S tends to 0 G of S. So if G of S is type 0, what is Kp? You understood the point. G of S is of this form. This form. Type 0 means there is no S term, no. If I add S here, then that is called type 1. I'm not adding any S here means type 0. So if it is type 0, right, if it is type 0, then what would be the Kp? Kp is 0 or infinity?
KP would be 1, sir.
Constant it is.
Yes, sir. 1 plus
1.
1 by 1. Type 1, sir. In G of S, if limit it is tending to 0 means we will be getting 1, sir. Okay, K is present, so K, sir.
So it is K.
Constant.
Correct? No. So it is K. That means if it is having any constant form, then this is 1 by 1 plus K. That means what? If input is a step signal, there is a finite error exists. Okay. Right. So now input is step. Now if I have this as type 1, so when it is type 1, which is k into 1 plus sta 1 plus stb by 1 plus st1 1 plus st2, if this is this form type 1, if g of s is type 1, then
Zero error.
kb is infinity, no?
Yes, sir.
Yes, infinity.
When kp is infinity, what is the steady state error?
0.
0. Means what? If input is a step signal, the output will reach its final value when t tends to infinity, correct? No? No error means what? Output is equal to input, no?
Yes, sir.
Yeah. So when type increases, error reduces. Can I say that? Okay, okay. Now, if it is type 2, what is error?
0 only, sir.
0. Right. So, when type is 0, when type is increased, error is becoming less. Yeah. So, give me only 1 minute. So, let us try to do it for unit ramp. Unit ramp. Unit ramp means limit s stands to 0. S r of s by 1 plus g of s. So r of s is, what is the value of r of s here? What is the expression for steady state error? Yes or no? So this is what the expression I get, no? So this is called positional error. When input is step, we call it as KP, positional error, and we call it as velocity error constant. So this is called a velocity error constant. ESS is 1 by KV. Right. So now, if G of S, if it is type 0 system, what is KV?
0.
No, 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 no. If it is type 0, what is KV? G of S is K into 1 plus 1 plus STA 1 plus STB by 1 plus ST1 1 plus ST2. Right. So this is G of S. If G of S is having this, what is KV?
0, sir.
0. So KV is 0. When KV is 0, what is steady state error?
Infinity.
Infinity. Means your output will not reach your output will not reach your input if then there exists infinite error if it is type 0 system. This is all right. Okay. And now if it is type 1 system, if it is type 1, you will be getting S here. The moment you will be getting S here, what is KV?
K.
Constant. K.
Constant. What is error? Constant
1
error.
by K.
1 by KV. Right, 1 by K. Sorry, 1 by K. Now, if it is type 2,
Zero.
what is KV?
Error is 0.
Infinity.
Infinity. Error is
0.
0. So when type increases, what is happening to error?
Decreases.
Minimizing.
Decreases. When type increases, error decreases. So if type of the system increases, error is what decreases. So type 0, type 1, type 2 and all. So this is what unit RAM. Right. So only small thing is there, that is called, when unit is parabolic is what we can consider and we will analyze. I think by this time, I think we encroach into another period. So you have another period at 10 o'clock, right?
Yes, sir.
Yes, sir.
So if you have any questions, you can ask me, or otherwise we can meet in the next class.
Sir, when is the minor, sir?
So you want me to conduct minor before mid or after mid? Your wish.
Is it possible to do it on same day of mid, sir? Yes, sir.
So we will conduct mid and then minor, or minor you ask me to conduct before Monday or Monday sometime.
No, sir. On the same date of mid exam at 11 o'clock at that time, morning.
All right for me. No problem.
Okay, sir.
Okay, Dheeraj?
Okay, sir.
Is it fine for everyone conducting minor and mid both on same day?
Yes, sir.
Okay. Then on the same day we will be conducting the exam. Okay? Fine. So if you have any questions, you can ask me, or otherwise you can leave. Thank you.